Hello everyone and welcome back to the Ionic Compounds lecture series. Let's take a look at our next section, which is polyatomic ions. So a polyatomic ion is multiple atoms bonded together in a charged, meaning ionic, molecule. Okay, so we'll talk about molecules next time, but what we mean is just a grouping, right? It's a compound bonded together by covalent bonds instead of ionic bonds. So let's take a look at some that are common, such as NH4+. This is what we call ammonium. And as we can see, there is more than one type of element in this ion. So it's a polyatomic ion, more than one type of atom. And the way that this is bonded together, I like to show my students because it gives us a clearer picture of what's actually happening in this ion. Nitrogen is in the middle, covalently bonded, which again we'll talk about covalent bonding later. Covalently bonded, but we represent that with a single line, to 4 hydrogens. And there is a positive charge on that nitrogen. Okay. Another common, and this is a +1 charge, right? Another common polyatomic ion with a -1 charge would be nitrate. NO3-, nitrate. Nitrate looks like this. There are 3 oxygen atoms bonded to a nitrogen. There's a negative charge on each of the oxygens and a positive charge on the nitrogen. Okay. A 2- example would be sulfate. SO4, 2-. Sulfate looks like this, with the sulfur bonded to 4 oxygens, and each of those oxygens has a negative charge. Each of those singly bonded oxygens has a negative charge. Okay, so that's where the overall charge of 2- comes from up here, right? Up here, nitrate, 2- charges and 1+ charge. Overall, the charge of nitrate is a -1. Another common 2- ion is carbonate. Carbonate looks similar to nitrate. It's got carbon in the middle with 3 oxygens bonded to the carbon. 1 double bond and 2 negative charges on each of those single bonded oxygens. All right, giving the overall charge of 2- for carbonate. A common 3- charge polyatomic ion is phosphate. PO4, 3-. And when we draw out the structure of phosphate, so these are the chemical structures, right? These are the chemical formulas up here, right? Again, symbolic representations of these polyatomic ions. Phosphorus is in the middle of 4 oxygens. Oops. There are 3 oxygens that have single one single bond to phosphorus, and one oxygen with a double bond. Each of the single bond oxygens have a negative charge, and so the overall charge for phosphate is 3-, 1 for each of those negative charges on the oxygens. So you won't be required to memorize these, right? For the polyatomic ions, you won't be required to draw them, but I think it's important just to give us a clearer picture of what we mean when we just write down, right, the chemical formulas for these polyatomic ions. Okay, so let's get right to naming. Let's name some polyatomic ions in chemical formulas in ionic compounds, right? Because these ions like to match up with an ion of an opposite charge. And so let's name calcium carbonate. Okay, CaCO3. So this ion here, right, what we're going to do is figure out which are present, right? So I did just say the name earlier, but it's okay. Let's take it apart, right, and figure out how we came up with calcium carbonate. So we're looking for polyatomic ions. The way that we can figure out if one is a polyatomic ion is if the letters are uppercase, right? Carbon, uppercase C, oxygen, uppercase O, right? If this was a lowercase o, that would be a different thing. That would be cobalt, right? The element. So when we see uppercase letters together, we know that we're going to be talking about a polyatomic ion. That's at least one way to tell. Okay, so we know that that's carbonate because we can look in a list that we have and figure that out, which I'll show you in a second. And this right here, this is an uppercase C with a lowercase a, so we know that is an element. That's calcium. So this is calcium carbonate. Again, all lowercase, and there's a space in between the calcium and the carbonate, right? The cation and the anion. If we break this apart into the cation and the anion, we get calcium carbonate. The charge on carbonate is 2-, and the charge on calcium is 2+. And we can tell that by looking at the periodic table. Calcium is in group 2A, right here. Okay, so let me show you the image that lists out the common polyatomic ions. Okay, so starting at the top left, the only positive one, the 1+ ion that we'll really be seeing is ammonium, and we've written that up on the board already. Going across to the right, we see carbonate is listed in the group where the charges are 2-, right? And then next to it, with a 1- charge, is hydrogen carbonate. So all that's been done is an H+ has been added to carbonate. So now the overall charge is -1 instead of 2-. When we go down that column in the 1- charge area, we see acetate and cyanide. And then that wraps it up for the carbon-based polyatomic ions. Down below cyanide, we see the phosphorus-based polyatomic ions of dihydrogen phosphate, hydrogen phosphate to the right, and phosphate to the right of that. We can see that from phosphate with a 3- charge, hydrogen phosphate has 1 hydrogen added to it, and then dihydrogen phosphate has 2 hydrogens added to phosphate. Each time a hydrogen is added to a polyatomic ion, the charge increases by 1, meaning it gets less negative by 1, because each time an H is added, it's actually thought of as H+. So that's why you see the charge is changing each time. Down below dihydrogen phosphate, we see hydrogen sulfate. That is nothing more than just sulfate to the right of it with an extra H+, an extra H, an extra hydrogen added. And so again, we see the charges changing from sulfate 2- to hydrogen sulfate 1-, having the charge increase, meaning increase on the number line. Okay, getting less negative. And so down below sulfate, we see sulfite. So this ITE ending means that compared to sulfate, there is 1 less oxygen. So we also see that trend for if we go up to the top left of this chart, nitrate has 3 oxygens and nitrite has 2 oxygens. So the ATE, ITE name ending, that's how those change. Back down to the bottom, we see the oxygen-based polyatomic ions of hydroxide with an oxygen and a hydrogen covalently bonded together with a minus charge, and then peroxide. And so peroxide is more than one atom, but it's actually the same element. Peroxide is 2 oxygens bonded together with an overall 2 minus charge. Still polyatomic though. Permanganate is the one on the bottom left-hand column, and the per means that there are the maximum amount of oxygens bonded in that polyatomic ion, and the manganate comes from manganese, Mn, that element. All right. Now, let's do another example. Let's name SnSO4. Okay, so the way that we're going to do this is first we want to figure out if our cation is a variable charge metal. Up here, calcium we saw was in group 2A in the periodic table, so calcium is not a variable charge metal. Tin though, let's make sure. Let's look at our chart right here. We do see that tin is one of the variable charge metals on the bottom right hand side of these transition metals. Tin can either have a 2+ or a 4+ charge. So let's figure out which one it is in this case. All right. So again, we're going to proceed the way that we learned before, where we have to figure out the charge on the anion first. So let's do that. All right. Sulfate, or rather, I should get there, SO4, right? We call that sulfate, right? So we know that the last half of the name is going to be sulfate. We know that for sure. It's the polyatomic ion. Let's figure out which tin this is, though. Is it going to be tin 2 or tin 4? We have to figure out the charge on sulfate, so let's write that down here. And now let's write out all the pieces. We have tin, and there's one of them. Sulfate, and there's one of the whole sulfate. So in order to cancel out the charge of 2- on sulfate, what must the charge on the tin be? Right, it must be 2+. Okay, so this overall name is tin 2 sulfate. Okay, so a throwback to what we were just talking about earlier. By the way, calcium carbonate is chalk, seashells, limestone, aragonite, the mineral, and it can be found in tums. Okay, so calcium carbonate is a very common naturally occurring mineral. Now let's look at another example. Let's write the formula for ammonium phosphate. Oops, number 3. Ammonium phosphate. Okay, so this time we know which ions we're going to be working with. We've got ammonium, which is right up here. It's a polyatomic ion, ammonium, NH4+, and phosphate, PO4 3-. Okay, so working like we have before in the previous lectures, let's figure out how many of each ion are needed in the formula to cancel out the charges. Well, we've got a 3- here and a 1+ here. So how many ammoniums are needed to cancel out the 3- charge on the phosphate? Right, 3 total are needed. So this overall positive charge is 3+, and this negative charge is 3-, right? This is a zero net charge once we bring them together in the chemical formula. How many ammoniums are there? 1, 2, 3. How many phosphates? 1. All right, so let's write the chemical formula down here. NH4. And there are 3 of them. Hold on. What do we do in this case? If we say that there are 3 ammoniums, this looks like there's actually 43 hydrogens, doesn't it? So, a really important thing to remember about polyatomic ions is that if there's more than one of them, we have to use parentheses around the polyatomic ion so that this little number applies to the entire thing and not just to the atom itself before it, to the single atom before it. All right, so then there is 1 phosphate, PO4. This is the chemical formula for ammonium phosphate. And let's make sure that we write that rule over here. Use parentheses, or we'll say write parentheses. Around more than 1 polyatomic ion. Right? These parentheses here, right? There's 3 of them, so we have to write parentheses around those 3 ammoniums. We do not need parentheses around this phosphate because there's only 1 of them. So we only write parentheses around more than 1 polyatomic ion so that we can enclose all of those atoms of the polyatomic ion together and multiply by 3 in order to cancel out the charge and get a net charge of 0. So go ahead and work at the concept check, and thank you for watching.